So my mission is to use living human brain to understand what goes wrong in Alzheimer's disease. My research has been funded very generously by Race Against Dementia and the James Dyson Foundation, and that's enabled me to establish a world-leading live human brain system to study Alzheimer's disease. We work with neurosurgeons here at the University of Edinburgh, and effectively some individuals need to have operations to remove brain tumours. The surgeon will need to go in and remove a little bit of the brain on top to access that tumour safely. With the permission of the patient and the University of Edinburgh, we can take that to my lab. Now, synapses are the connections between nerve cells that allow them to communicate. So in dementias, these connections die, but we don't know exactly how they die. But what we really need to do is understand what's happening on a cell and molecular level, taking toxic protein that's been extracted from people who've died with dementia, adding those to living human brain slices, and watching in real time how this disrupts the synapses. When we look at a microscopic level, are these two proteins that seem to go awry. Amyloid Beta, that forms these large clumps called plaques in the brain. And the second is a protein called tau that forms these structures inside cells called tangles. An increase or a decrease in A-beta both result in synapse loss. Talking to the engineers at Dyson, you learn a huge amount about what's out there in the engineering field and think, well, how can I apply that to my own research? So the current work that we've got in progress, like what's immediately next, my team are working on strategies of live imaging synapse loss. So some of the images I showed you, they bind to the brain and we're looking at sort of downstream path. We want to watch this in real time. And actually studying the difference between the two processes could help us uncover new treatments. So we're very excited by these differences that we've seen coming through. So using the tools that we've developed with Alzheimer's disease, we can expand these to other brain diseases and also learn where there's similarities and differences and potentially expand the model even further.
Congratulations on the work. I mean, it is world-beating stuff, this.
We're
really ahead.
I mean, it feels really nice to be at the forefront of a technique that we can use to apply to so many different things.
You're making amazing discoveries.